Bismillahirrahmanirrahim. Dear students, let's solve another problem using the direct method for SFD and BMD plotting. And in this problem, we will learn how to deal with UDL in case of direct method. So let's see. This is problem number 2 of this week. And in this problem, and this is again one of the problems that we have solved previously using the method of equation. Okay, so we have a simply supported beam that is subjected to a UDL and a point load. Point load is of 15 kilonewton magnitude. The intensity of UDL is 5 kilonewton per meter, and we have a point moment acting at point A. Magnitude is 80 kilonewton meter. This point is B, this point is C. We'll have two reactions. These distances are 5 meter and 5 meter. This is RA and this is RC. So this is the given problem, and our objective is the same. We want to draw shear force and bending moment diagrams. The first step is to calculate the reactions, and as we discussed earlier, no matter which method of plotting of SFD and BMD you are using, the reaction calculation remains the same. Okay, so we will apply sigma Fy equal to 0 with upward forces as positive, Ra plus Rc. These are the two forces acting in the upward direction, both are reactions, and then we have minus 15 kilonewton force acting in the downward direction, and resultant of the UDL is minus 5 into 5, and this should be equal to 0. If we rearrange this equation, we get Ra plus Rc equal to 40. Let's call this equation as equation number 1, and then we can apply second condition of equilibrium, sigma mc equal to 0 with clockwise movement as positive. So how many forces are generating movement about point C? If we start from end A, so Ra is producing movement in clockwise direction. Ra into 10, and then this movement, which is of 80 kilonewton meter magnitude, and it is in clockwise direction, so it should be taken as positive 80. And then this point load 15 kilonewton, lever arm is 5, and it will produce movement in counterclockwise direction, so negative 15 into 5, and then resultant of this UDL, which will be acting somewhere over here, and the magnitude of the resultant will be 5 into 5 equal to 25 kilonewton. So, and it will produce movement in counterclockwise direction, so it will be negative. Minus 25 is the magnitude of the resultant, and the lever arm is 5 by 2. This should be equal to 0. So if we solve this equation, we get Ra equal to 5.75 kilonewton. Okay, so this is Ra, and if we plug in the value of Ra in equation number 1, we get 5.75 plus RC equal to 40. This implies RC is equal to 34.25 kilonewton. So in this way we have calculated both the reactions RA and RC, and both reactions are positive, which indicates that the assumed directions of these two reactions is correct. Okay, now once again, in this direct method we don't have to go into that cumbersome procedure of writing down the equations for all the portions. Rather, once we have the reactions, we will directly jump to the plotting of SFD and BMD. So let's see how that can be done. So let me draw the beam here. So we have a simply supported beam subjected to a UDL in half of the span. Oops. Okay, intensity of UDL is 5 kilonewton per meter, and we have a point load acting at this point with a magnitude of 15 kilonewton. This point is A, this is B, this point is C. Reaction at support A, RA, is equal to 5.75 kilonewton, and reaction at support C is equal to 34.25 kilonewton. And this is 80 kilonewton meter moment. Anything else? We can mark these distances as well. 5 meter and 5 meter. So this is the given beam. Now I think I have marked all the required information on this diagram. So in order to plot SFD and BMD, now we will draw the guidelines. Okay. And we know that we draw guidelines corresponding to every point where we expect a change in shear force or bending moment. So let's draw the shear force diagram first. This is our 0, 0 line. SFD in terms of kilonewton. Okay. So at point A, which force is acting? This RA is acting in the upward direction. So this will bring SFD to a value of 5.75 here. 5.75. And then is there any force from point A to point B? No, there is no force. So the shear force will remain constant in this region. 5.75. Okay, and then at point B there is a point load acting in downward direction with a magnitude of 15 kilonewton. We are at positive 5.75. So from this, if we subtract 15, what do we get? We get 9.25. So this brings shear force diagram to 9.25. And now in portion BC we have a UDL. We have not dealt with a UDL in this direct method before. Now if we look at the relationship between applied load and shear force, what is the change in shear? Change in shear is equal to the area of load diagram. So we will calculate the area of this load diagram, and that area will give us the change in shear. From point B to C, how much is the area of this load diagram? vertical dimension is 5 and the horizontal dimension is also equal to 5. So 5 into 5 is 25, and the load is acting in the downward direction, so we'll take it as negative. So minus 9.25 minus 25. This gives us what? It gives us minus 34.25. And for area load, the VDL, for area load, the SFD is always first degree. So this is first degree, and this point is 34.25 kilonewton. Whenever we have a UDL, SFD will be first degree. And at this point, we have magnitude of 34.25, and how much is the reaction? 34.25, and it's acting in the upward direction. So this reaction will bring SFD to 0. So finally, shear force diagram will close. This part of SFD is negative and this part of SFD is positive. So shear force diagram is closing, which means that shear force diagram is most probably correct. And once we are done with the entire solution, then I'll compare these diagrams with our previously drawn diagrams as well. Okay, so this completes SFD. Now let's move to the bending moment diagram. This is 0, 0 line, and we are plotting BMD, and the units are kilonewton meter. Now, as I said earlier, that the presence of a point movement or a couple does not reflect in shear force diagram. So we have to keep an eye on the load diagram as well. At point A, 80 kilonewton meter movement is acting, and this 80 kilonewton meter is in clockwise direction. So according to our convention, as we are drawing the shear force diagram from the left side, so clockwise movement is positive. So we reach at positive 80 kilonewton meter. And then the magnitude or the change in BMD is equal to the area of SFD. So plus 80 plus this area. And how much is this area? 5.75 into 5, which is 28.75. So 80 plus 28.75, and this gives us 108.75. And SFD is first degree, so SFD is 0 degree, so BMD will be first degree. So we will draw a straight line here. And then we are at positive 108.75, and this area of SFD is negative, and this is a trapezoidal area. So how do we calculate the area of a trapezoid? Area of trapezoid is sum of parallel sides into the perpendicular distance between parallel sides divided by 2. So let me show it here on paper. How do we calculate this? This area of trapezoid will be 9.25 plus 34.25. This is the sum of parallel sides into the perpendicular distance between parallel sides, which is equal to 5 divided by 2. This is the area, this is a formula for area of trapezoid, and if we solve this, what do we get? We get 108.75. So this area is exactly 108.75, and it is negative. So from this 108.75, when we will subtract this area, we will reach at 0, which indicates that the diagram is closing. And in this case, the shear force diagram is first degree, so bending moment diagram will be second degree, and we'll have to see that what should be the slope of bending moment diagram as we move from left to rightward direction. As the magnitude of the shear force is increasing, so the slope of bending moment diagram should also be increasing, which means that we should draw a curve something like this. So this is second degree line. We need to write it down here with convex up, and the entire bending moment diagram is positive. The entire bending moment diagram is positive. So this completes the bending moment diagram and it is closed, which means that this diagram is correct. Now let me compare this solution with our previous solution. Here is the solution of the same problem that we solved earlier using the method of equation, and you can see that our shear force diagram and bending moment diagrams are exactly the same. Let me try to fit in them in the same frame. Probably it's hard, but anyways, this is our current solution and this is our previous solution. The shear force diagram and bending moment diagrams are exactly the same. So once again, we have observed that if we follow a correct method, then always we will get correct shear force and bending moment diagrams using this area method or method of equations. Okay, so this completes our problem number 2 of this week. So I will just stop recording here. Thank you very much.